Today we are going to discuss bias detection in AI models, and fairness metrics in AI systems, from the perspective of architecture, data, optimization, and deployment. I will assume you are technically mature, comfortable with machine learning pipelines, and familiar with statistical reasoning, but I will deliberately keep the language plain and conceptual. The goal is not to impress you with notation, but to sharpen your structural understanding. Let us begin with a simple but powerful observation. AI systems do not operate in a vacuum. They are trained on historical data. Historical data is a compressed record of human decisions, institutional practices, economic structures, and social inequalities. When we train models on that data, we are not just learning signal. We are also inheriting patterns of bias embedded in the past. Bias in AI can be defined as systematic and unfair discrimination against certain individuals or groups relative to others. The word systematic is important. Random errors are not bias. Bias is directional and persistent. It affects outcomes in a structured way across repeated decisions. To understand bias, we must decompose the AI lifecycle. There is data collection, data labeling, feature engineering, model selection, optimization, evaluation, deployment, monitoring, and feedback loops. Bias can enter at any stage. Start with data collection. Suppose you build a hiring model trained on past hiring decisions. If historically a company hired disproportionately from certain universities or favored one gender over another, that pattern will be reflected in the dataset. The model does not know what is fair. It only sees statistical regularities. If certain demographic groups appear less often in positive outcomes, the model may learn to assign them lower scores. Next is sampling bias. Your training data may not represent the real-world population. If you train a facial recognition system on images that are mostly of light-skinned individuals, the model may underperform on darker-skinned individuals. This is not because the algorithm is malicious. It is because the data distribution is skewed. Then we have measurement bias. This occurs when the variables used to represent reality are themselves imperfect proxies. For example, using arrest records as a proxy for criminal behavior encodes policing patterns, not necessarily actual crime rates. Measurement bias is subtle and often overlooked because it hides inside the semantics of features. Label bias is an source. If human annotators label data with subjective judgments, those judgments may reflect implicit stereotypes. For example, labeling resumes as strong or weak may be influenced by names that signal ethnicity or gender. Algorithmic bias can also arise even when data is balanced. Optimization procedures minimize a global loss function. That loss function often averages errors across the entire dataset. If one group is a minority, reducing error on the majority group may dominate the objective. The system becomes very accurate overall but systematically less accurate for the minority. Deployment bias is the final layer. A model that performs well in a controlled environment may behave differently when integrated into a real system. Users interact with it, adapt to it, and change their behavior. Models' predictions can influence the very data it will later be trained on. This feedback loop can amplify bias. Now let us move from sources of bias to detection. Bias detection is not a single test. It is a structured auditing process. It involves identifying protected attributes, defining comparison groups, measuring disparities, and interpreting results in context. Protected attributes typically include characteristics such as gender, race, age, disability status, or religion, depending on jurisdiction and domain. Even if you do not explicitly include these attributes as features, they may be indirectly encoded through correlated variables. Zip code can correlate with race. Employment gaps can correlate with caregiving responsibilities. The absence of explicit demographic variables does not guarantee fairness. Bias detection begins with disaggregated evaluation. Instead of reporting one global accuracy number, you compute performance metrics separately for different groups. You look at true positive rates, false positive rates, precision, recall, and calibration across groups. The key is comparison. Are errors evenly distributed or concentrated? One fundamental fairness concept is demographic parity. This notion asks whether the rate of positive outcomes is similar across groups. For example, if a loan approval model approves 60% of applicants overall, does it also approve roughly similar proportions across demographic groups? If one group is approved at 80% and another at 30%, there is a disparity. However, demographic parity can be misleading. If the underlying qualification rates differ due to structural inequalities, enforcing equal approval rates might require approving less qualified candidates from one group or rejecting more qualified candidates from another. This leads us to a deeper discussion about competing fairness definitions. Another widely discussed concept is equalize odds. This idea focuses on error rates rather than outcome rates. It requires that the model's false positive rate and false negative rate be similar across groups. In other words, the likelihood of incorrectly approving or incorrectly rejecting should not depend on group membership. A related notion is equality of opportunity, which focuses specifically on true positive rates. It requires that qualified individuals have an equal chance of being correctly identified, regardless of group. In many high-stakes domains like hiring or admissions, this criterion is considered morally appealing because it emphasizes access for those who meet the standard. There is predictive parity, sometimes discussed in terms of precision. This criterion requires that when the model predicts a positive outcome, the probability that the prediction is correct is similar across groups. In a risk-scoring context, this would mean that a given score corresponds to the same actual risk level for all groups. At this point, you must confront an uncomfortable but mathematically grounded reality: not all fairness metrics can be satisfied simultaneously when base rates differ between groups. Base rates refer to the underlying prevalence of the outcome in each group. If one group has a higher average default rate on loans, for example, then equalizing error rates and equalizing predictive values at the same time becomes impossible under certain conditions. This impossibility result forces practitioners to make normative choices. Fairness is not purely technical. It is partly ethical and legal. The choice of fairness metric depends on context, values, and regulatory constraints. Beyond these group-level metrics, there is also individual fairness. The guiding principle is that similar individuals should be treated similarly. Difficulty lies in defining similarity. Similar with respect to what features? Who defines the distance function? In high-dimensional feature spaces, measuring similarity in a meaningful and fair way is extremely challenging. Another concept is counterfactual fairness. This asks whether an individual would have received the same prediction in a counterfactual world where their protected attribute had been different, holding other factors constant. Implementing counterfactual fairness often requires causal models. You must model how protected attributes influence other variables and predictions. This moves us from statistical correlations to structural causal reasoning.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.